So, all right, we're a bit behind. We're quite behind. So, let me ask you, if we're a bit late today, does that matter to anybody, or do people need to go immediately? Doesn't matter? Maybe about 15 minutes? Okay. All right. So I think we'll just finish this quickly, and then we'll go on to the DFT part, and then we'll be back on track. But I think we'll be about 15 minutes late. Okay. So what we need to do is we've talked about quantum mechanics, just background quantum mechanics. We've talked about crystals. Now we need to connect quantum theory with crystals. Okay. So we've basically got two separate pieces that we now need to pull together in order to understand how we're going to do some calculations of crystals. And so the way we're going to do that is we're going to firstly have our lattice, right? And we're going to say, well, if I want to make a macroscopic crystal, a real piece with Avogadro's number of atoms in it, billions of atoms, what I do is I take my lattice with its symmetry operations and I basically use it as a motif to print every single cell in my macroscopic piece of lattice, and then I get my crystal. So why can't I just do that for the wave function as well and the potential, right? Why can't I just say, well, I'm going to do a calculation in that box, okay, and I'm going to have my wave function around each of these atoms, and I'm going to have some molecular wave function and some molecular wave functions, and I'm going to get it. I'm going to do my converged calculation, and then I'm going to do exactly the same trick. I'm just going to take it like a motif and wave function, wave function, wave function, wave function. Okay? If that was all I need to do, then it's easy, isn't it? Because all I need to do is a calculation in one cell, and I can get the wave functions of the entire crystal, the macroscopic crystal. Except it doesn't work. Okay? And the reason is because of the Brillouin zone. So, and we can just do it in 1D. If you imagine a crystal, okay, this is a 1D crystal. Okay, we've got a cell periodic part of our wave function. I can draw a low frequency wave, a low frequency electron wave in this crystal. All right, so I can say I've got a wave which goes over, say, 3 atoms before coming back again, right? But my cell periodic part is not periodic, right? It's not periodic. So if I take that and just go stamp, 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 I do that calculation and I do the stamp, 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 all I'm going to get is it's not the same, right? And okay, maybe maybe it's going to look more like that actually, but it's still not that. That low frequency electron wave can exist in the crystal. There's no reason why it can't exist. In fact, if you think about the gamma point is 0 frequency, which is effectively infinite wavelength. Okay, so it's a very, very long wavelength electron wave in your crystal. And then once you go from the gamma point to gamma point plus delta, small distance away from the gamma point, what we have is not an infinite wavelength electron wave, but just a very, very long wavelength electron wave. And you cannot represent an infinite or long wavelength electron wave just in terms of one piece of cell periodic wave function. Okay? So how do we do it? The way we do it is we split our wave function into a cell periodic part and a crystal part. Okay? This is Bloch's theorem. Okay? So effectively, what we say is these cell waves, okay, is these cell waves are plane waves that exist in our cell. Okay, they're not cell periodic. They're not periodic in our cell, but we have a wave function in our cell periodic part, which is periodic, and then in total, this. I need to rub some of this stuff up. In total, this is our wave function. All right, and what we can see is if we want to get the wave function of the entire crystal, we need to consider all of the possible electron waves which can exist in our crystal. So we need a sum here, okay, and we're going to sum over k, right? We're going to sum over all possible k's in our Brillouin zone. And so when you're doing DFT of a crystal, and somebody says, "Have you done k-point sampling? You know, have you converged with respect to k-points?" That's what they mean, right? It's k-points are important because if you just do one k-point in a crystal and you have a single unit cell, your wave functions will not look like the wave functions of the whole crystal because you're not allowing low frequency electron waves to exist in your crystal. Okay? You have to obey Bloch's theorem. All right. So Bloch's theorem that okay. So this is for a single k point, but if you want the whole wave function of the crystal, you need to sum over all of the k points. Okay? And this is known as k-point sampling or Brillouin zone sampling, or any of the other things that you'll hear in codes like CASTEP or VASP or other plane wave codes, right? It's always k-point sampling, right? Right. So we talked about that from two different points of view. There's k-points for looking at band structures, right? So particular symmetric k-points like the gamma point, the x point, the k point on the band structure. That's what they represent. And there's also k-point sums in DFT. Now, I don't think we have enough time to look at the Kronig-Penny model, unfortunately, but I'll just describe it in words very briefly. We've sort of looked at some solutions to the Schrodinger equation for 1D potentials and 3D potentials, but none of them have been periodic, right? Our crystal is periodic. We keep saying it's periodic. So can't we solve a 1D Schrodinger equation which is periodic? And yeah, you can. So this is known as the Kronig-Penny model. And so what we effectively have is a bunch of delta functions, okay, periodically arranged on a 1D grid. And so we effectively have a free electron model between the delta functions, and then we have a delta function, which is our potential. Okay, so you can solve this in two pieces, just the same way you would solve like a step function Schrodinger equation. And what you find is, if you apply the Schrodinger equation to wave functions that look like bands, right? What you find is that you get band structure and you get electron mobility. So it's a model for a crystal, right? And you can extend the Kronig-Penny model from delta functions to having some potentials with some physical volume, some physical dimension, right? And of course, what you get is a wave, and then you get some amount of tunneling, some amount of wave, some amount of tunneling, some amount of wave. And this is a very simple model of a crystal, and it's the simplest model with a periodic potential that you can solve analytically, at least in the limiting cases, which exhibits band gaps. Okay, so even with a model this simple, you can see the difference between an insulator and a metal. Right? So when we think of a metal, we think that the there is no distinction between conduction bands and valence bands. Okay, so electrons can basically migrate from bound states into states which span the whole crystal, delocalized states. Okay, and so they can move and tunnel through the barriers, and so you get no band gap. On the other hand, if you have an insulator, you have that energy penalty from going from the valence band to the conduction band, right? And that comes just from this in 1D. You can see already band structure, right? And I think that's enough of this, right? So blah blah blah. I think we will. If anybody wants to talk more about the Kronig Penny model, then we will do that another time. All right. The rest of this stuff is just a little bit more about solid state physics, basically. It's in the notes if you want to see it, or you can speak to me about it. But now, finally, a little bit late, we're on to DFT, right? So this is what we were supposed to be doing mainly today, and hopefully we'll be able to catch up tomorrow. Right. Okay. So we've done crystals. We've done 1D systems, Schrödinger equation of the hydrogenic atom. But we want to do many atoms. Okay, we want to do many atoms. So the first thing you would try to do, naively, is to set up a many-body, multi-particle equation, right? A multi-particle equation of motion, which is the Schrödinger equation. So the Schrödinger equation of many particles. So it's the same as before. We've got a Hamiltonian operator. We've got energy eigenvalues, okay, and we've got wave functions, except now our wave functions have 3 n degrees of freedom. So if we have n electrons, so let's say we've got, let's say we've got helium, right, He, with 2 electrons, okay, then we've got 3 n electrons. Helium has 2 electrons, so we have 6 degrees of freedom. Okay, 6 degrees of freedom is very, very difficult even to represent mathematically. Okay, do I represent this? Right, yeah. So we've got exponential growth in the number of in the dimensionality of the wave function. So, you know, once you go to 3 electrons, you've got 9 degrees of freedom. Okay, this is a huge dimensionality. And you've also got to contend with the number of interactions between all of the electrons, and also even between the interactions between the electrons and the nuclei is growing quite a lot as well. And we have all of these high-dimensioned integrals that we certainly cannot solve analytically. We're going to have to solve it numerically, even if we could represent it. So I don't think I've written that down, but I will say, let's say we've got an atom, an electron, right? And we have that electron in 3 dimensions, so it's got a state vector x, y, z. Okay, that's 1 electron. Now, I have another system where I have an atom and I have 2 electrons, and now I've got x1, x2, x3, x4, x5, x6. Right? These are my two electrons. Excuse me. How can I represent that in a basis? The first case is easy. I have a 3D space, and I can divide space into a grid. Right? So I'm going to get really good at drawing cubes. Right? So I'm going to take a cube, and I'm going to just divide this into a grid in 3D, and I'm going to say, where is my electron, or where is my electron density in this grid? Okay, it's in this grid. I have, 1 unit in this grid point. I have 2 units in this grid point. Whatever. Okay, how do I do that if I have 2 electrons? right? How do I do it? Because now I have 6 dimensions. It's not that I just have that for one electron and another 3D grid for the other electron. No, right? Because it's one 6-dimensional wave function. This is my Hilbert space, right? So instead, actually what I have is, if I go to 4 dimensions and I divide space in the same way, so I have this thing, that's my grid. I'm just going to draw it like this, right? That's my grid. But now I'm going in this dimension, right? Now that dimension is another one of these, right? Right? And then, so I'm dividing that dimension, but every time that I divide that dimension, I've got one of these. That's only 4 dimensions. Once I've divided that dimension into, say, 10 of these, right? 10 3D divisions in the 4th dimension, then I've got to take those 10 3D divisions in the 4th dimension and divide it 10 more times into the 5th dimension, and divide that 10 more times in the 6th dimension, right? So if I've divided space, say, 10 times in X, 10 times in Y, 10 times in Z, right? Then I've got 10 by 3, right? But if I've also divided 10 times in the 4th dimension, and then 10 times in the 5th dimension, and then 10 times in the 6th dimension, when I go from 1 electron to 10 electrons, even to divide my space into 10 divisions in each dimension, I have 10 to the 6 points in space. This is not a very fine sampling of space, right? If I go to 3 electrons, you can see very clearly that by the time I get to something useful, like, I don't know, silicon, if I look at silicon and I've got to be doing tens of electrons in a silicon calculation. Once I have 2 silicon atoms, I will have more points in my division, in my number of degrees of freedom, in 2 silicon atoms than there are grains of sand on the Earth, right? If I look at 3 or 4 silicon atoms, I will be having more divisions in my multi-dimensional wave function than there are points in the observable universe, right? Atoms in the observable universe. It is impossible not only to solve the many-dimension Schrodinger equation, it's impossible to even represent it on a computer at a fairly coarse accuracy, right? It's simply impossible and will always be impossible. Okay, maybe quantum computers, right? But with normal classical computers, we can't even store this object. Right, so we've got some other techniques, right? These are so-called isomorphisms of quantum mechanics. They are ways of writing quantum mechanics mathematically, which give you this same mathematical result, but have a different approach to solving the problem. Okay, and there's 3 possibilities here, right? That I've just plucked out of the possibilities. There's many isomorphisms of quantum mechanics, but quantum Monte Carlo is one possibility. You can basically solve the equations of quantum mechanics stochastically with random numbers, and you can sort of use random numbers like a kind of basis to build up an answer. Density functional theory, which is what we're going to talk about, which gets rid of the many-body wave function, or sort of steps around it. Mean field theories are approximate, and there's other isomorphisms as well, like Feynman's path integrals, which can be thought of as a type of quantum, can be solved in a quantum Monte Carlo way. There's loads of ways of doing this, right? And the techniques that we will typically see used in quantum chemistry and quantum solid-state physics are things like DFT, Hartree-Fock, at least in the sense of hybrid functionals, maybe quantum Monte Carlo, right? effectively what these are ways to solve many-body quantum mechanics without ever needing to worry about the many-body wave function. So what is DFT? DFT is what we're going to focus on, at least today. So DFT is a isomorphism. So that means iso, same, morph is Greek, right? Same, isomorphism, change, same change, right? So it's like quantum mechanics. It's changed. It's a bit different, but it's also the same. Okay, it's the same mathematically, but it's represented differently. So DFT is primarily used for running calculations of atoms and molecules, crystals, but DFT is also used in subatomic particle physics. There are calculations, DFT calculations run on nucleons, for instance. And it's a very important method in our fields. So very briefly, DFT came about in the 1960s because of Hohenberg and Kohn. And then Kohn and Sham in the following year came up with another type of DFT, which we'll go into. I should just say it. In 1964, the type of DFT was what we now call orbital-free DFT. So everything that we consider as part of the quantum problem is based on the density. But in 1965, it was recognized that it was impossible, or it was unknown how to calculate everything from the density. So they kind of relented a little bit and started introducing wave functions back into the picture. But not many-body wave functions, single particle wave functions. Right. So this resulted in the Nobel Prize in Chemistry in 1988 for Walter Kohn. John Popel also got it in 1988, but for quantum chemistry in general, not necessarily for DFT. But just because they got the Nobel Prize in 1988 doesn't mean that DFT was solved in 1988. Most of DFT theory, apart from the very fundamentals, has come about in the 90s and 2000s. Okay, it's an ongoing area of research, and it continues. It becomes better and better. Also, computers become better and better. Okay. Right. So where do we begin? We begin with the Hohenberg-Kohn theorems. Okay. So what they noticed originally was, okay, I can't make the many-body wave function, but I recognize that the potential in the many-body Schrödinger equation is 3D. Okay, I recognize that the density is 3D. Okay, so the dimensionality of the wave functions goes as 3n, 3 to the n, but the dimensionality of the density, the electronic density of the system and the electronic potential of the system remains 3D. Okay, so they asked the question, so if that's the case, can we calculate observables directly from the density or the potential? Okay, and so the first theorem establishes that the ground state properties of a many electron system, so basically a system of atoms with electrons, is uniquely determined by the electron density. They proved that if you have the electron density of a many electron system, then everything about that system, the state of the vector in quantum mechanics, is uniquely determined by the density, the electronic density. The second theorem introduces the variational principle to the concept of electron density. So effectively, if I change something about my my system, then I also change the observable. Okay, let me say that more clearly. So for instance, if I want to find the ground state energy of my system, okay, and I change the density, and I have some way of taking my density and calculating the energy, the so-called universal functional. So this is a functional that takes the electronic density and results in an energy. Okay, the ground state energy should be the lowest energy that I can possibly recover from putting a density into that functional. So if I try throwing random numbers into my functional, random numbers which represent a density. So let's say I've got, this density, and this density, and this density, right? You know, just 3 different shapes represented in some basis. Those are my densities, and I put those densities, that one, into this functional which takes my density, right? And it gives me an energy, right? The ground state energy of my system should be the lowest energy that I can possibly get if I put any density into here, right? So if I try every possible density that can possibly exist, only one of them will give me the lowest energy, right? The ground state energy. Okay? And so the variational principle establishes that I can throw a density into here, and I can find the gradient of the density with respect to the density, and the gradient of the energy with respect to the density. I can follow the gradient, and I can go down to the ground state energy. Effectively, I can find the ground state energy from the density if I have the functional, which maps the density to the energy. Right, so I have here some kind of, how can I say it? A sort of pseudo derivation of the Hohenberg-Kohn theorems, right? I think we're going to skip over this today, and you can see it in the notes or the slides, or if you're interested in it, we can go through it in paper if you want to. But I just don't think we have time today to go through the derivation of the Hohenberg-Kohn theorems, all right? Yeah. But in words, this is provable mathematically, right? We know that there is only one density, right, which represents everything about the system. One density represents everything about the system, and there exists a minimum energy which is found by finding the density which maps to the lowest energy. Okay? All right? And so if we take the derivative, we can follow the derivative and use the variational principle to find the lowest energy and the lowest potential together. Okay? The problem we face, the problems we face are that the Hohenberg-Kohn theorems only tell us that these things exist, right? They don't tell you what the universal functional is, all right? So that's kind of useless, really, because you can't take a random density, throw it into the functional, and find an energy, because you don't know what the functional is. You know it exists, but you don't know what it is mathematically. So they spent a while trying to figure it out, and they knew that they could calculate the Coulomb potential of the nuclei from the density. They can calculate the mean field electron-electron, or the so-called Hartree or interelectron Coulomb potential from the density. But they had no idea how to calculate the kinetic energy from the density. They had no idea how to calculate what's called the exchange energy, which comes from Hartree-Fock theory. No idea. Okay, it's not clear how to calculate those properties from the density. You know it must be possible, but it doesn't necessarily have to be analytic, right? So what was come up with was, okay, well, if we can't do it, if we can't write an analytic form for the universal functional in terms of density, can we come up with another system which maps onto to our system of many electrons? In effect, we have an interacting many electron picture, but can we get the same density from a system of non-interacting particles? Okay, so in effect, the question is, if you have electron, 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 okay, it's actually an electron density, but whatever. We have an electron density, And we know that that has a state vector associated with it. We know it has a density associated with it in three-dimensional space. The question is, can we recover the same density, so the density of that system, so I don't know what we're going to call it, but let's call it that, right? That's a many-body density. But can we also recover a same density from a series of non-interacting particles, right? So if we think about how we can write a density, you can write a density, let's say we've got a wave function of a non-interacting hydrogen atom. Okay, it's just one hydrogen electron. And we've got a position in space. Let's say we've got another position in space, I, j. We sum over all of these wave functions. And we say that's going to be equal to that. Let's put a star on there, right? The question is, if we have one hydrogen electron and we make a density, can we effectively say, well, that's one particle, and we're going to sum them in such a way that over all of the particles, we're going to recover the same density as the original many-body density? Okay, and the answer is yes, you can do it. You can mathematically formulate a system of non-interacting particles which has the same density, same electron density as a many electron interacting quantum problem. Okay, and so once you do that, what it really helps you with is the kinetic energy part of the functional. So if we write our kinetic energy part like this as a function of the density in the Hohenberg-Kohn picture, we don't know how exactly to write that. You don't know how to exactly write the kinetic energy in terms of the density. There are approximations, there are kind of power expansions that you can do, but they're not exact and they're often quite bad. However, once you write the density in terms of a sum of non-interacting states, which are basically wave functions, not one many-body wave function, but many non-interacting wave functions. So we've gone from a 3n dimensioned wave function to n 3-dimension wave functions. Right, so we've gone from 3n dimensions to n 3-dimension problems. Right? Of course, that's much easier to solve than that. In fact, that's much easier to represent than that. Right? And now you can simply write down the expression for the kinetic energy in terms of those non-interacting wave functions. Okay, and you can write the density, of course, in a similar way. Being able to write the density in terms of our non-interacting wave functions is important because all the other terms, like the Coulomb term, the nuclear term, the mean field inter-electron term, they're all written in terms of the density. So let's have a look. Right, so for instance here, we've got the Coulombic part of the potential. Right? So what this is giving us is the mean field interaction between an electron and the rest of the ensemble of electrons. Okay, and we can write that in terms of the electron density. Right? So if we're going to write our system in terms of a set of non-interacting states like this, we need to be able to get the density so that we can get the density dependent terms like this, this, and this. Right? Okay. So effectively what we end up with is a series of coupled interacting 3D Schrodinger equations. Okay, not one many-body Schrodinger equation, but a set of coupled 3D Schrodinger equations. Okay, which is something you can solve with this potential. Okay? And that is really all DFT is. It's not that difficult, except that we don't have a clue what that is, the exchange correlation, right? So when we said that we have, we've mapped the problem onto a series of non-interacting single particle states, and when we said we've the entire state of the system is represented in terms of the density, the electronic density, we still don't know how to calculate the exchange. So we said that our electrons are fermions, right? So these are anti-symmetric state wave functions, which means that if you switch the position or the energy level of two electrons, okay, the whole wave function must change sign. Okay, it's anti-symmetric. They're fermions. Okay, and so what that means is we get an energy penalty associated with that component called the exchange. Okay, we don't know how to represent that, and the correlation. Well, the correlation is basically the penalty we pay for representing everything in terms of a set of single particle interacting states, and the correlation is the energy difference between our approximate system and the real system, right? So because the exchange correlation is defined to be exactly the difference, this is an exact function, right? But we don't know the form of the exchange correlation, so in practice we necessarily have to approximate it. Okay, so DFT written like this is exact, but in practice it's not exact because you have to approximate the exchange correlation and you have to use a basis. Right, so implications. DFT enables us to predict things accurately, molecular structure and crystals, and it forms the basis for a wide range of other techniques. Okay? Most importantly, DFT is something we use because it's a good balance between efficiency, computational efficiency, and accuracy. No one's claiming that DFT is perfectly accurate and gives you the right answer every time. You always have to be careful with DFT. It can give you the wrong answer very easily, okay? Because the approximations we use for the exchange and correlation are inexact. Okay? But it's fast. Okay? There's other techniques that are very slow but more accurate. It's a balance. Right, so we've really got to speak about the exchange correlation functionals. So, exchange and correlation. Right, so the first point is, what is exchange and correlation? So we've said exchange is the energy penalty associated with switching a fermion either in space or in energy level. Okay, it's a quantum statistical phenomenon. Correlation, on the other hand, is basically just the difference between a many-body system, a many non-interacting particle system, and the full many-body interacting Schrödinger equation. Okay, so correlation was defined at the same time that they defined what Hartree-Fock is. Okay, so if you think about Hartree-Fock is very similar to what we've just defined, right? We have a kinetic term, which is in terms of the set of, that's supposed to be a set, the set of non-interactive wave functions, single particle wave functions. We have a Hartree potential in terms of the density, right? So the Hartree is the mean field interaction between electrons. And then we have the external potential, which is between the electrons and the nuclei, which is basically the 1 over R potentials. So we'll call this external of R. And in Hartree-Fock, the final piece of the puzzle is the exchange energy, the Hartree-Fock exchange. Right? And we'll talk about this maybe in 2 days, right? But the Hartree-Fock exchange is defined in terms of the set of wave function, non-interacting wave functions, and the exchange is everything, right? So that is the Hartree-Fock Hamiltonian, not DFT, Hartree-Fock. Okay, so right, the Hartree-Fock Hamiltonian looks something like that. Okay, and so what we have is an approximate theory which will approximate the energy of an atomic system. Okay, and it has some error associated with it. So I said I'm going to overrun. Sorry. So it has some error associated with it. The error in Hartree-Fock is called the correlation. It's just defined as the correlation. So plus the C of maybe we can write it in terms of the density. We don't really know. Right? Correlation. This does not exist in Hartree-Fock, and the definition of the correlation is the difference between Hartree-Fock and reality. Okay, that's what it is. Okay, so in DFT, the correlation is a slightly weird concept, right? Because it's not the difference between DFT and reality; it's the difference between Hartree-Fock and reality. Okay, so in DFT, the correlation really just means the error. It just means the error, because in DFT we also take what's called the dynamic correlation, which is effectively just the part of the kinetic energy which is approximated away by using a set of non-interacting single particle states, and put that into the correlation as well. So in DFT, the correlation is actually not only the correlation from Hartree-Fock, but it's also the kinetic energy error and any other error as well. Okay, so in DFT, just think of the correlation as the error. Okay, just think of the error. Right. So error. Right. So now the question is, can we calculate the exchange and correlation? Can you calculate it? Well, the first thing you've got to do is you've got to say, well, under what conditions am I going to calculate it? And so what they thought originally was, let's take the simplest quantum system and calculate the exchange energy for that system. The simplest quantum system is just having electron density the same everywhere in space, homogeneous, right? So if we have this space and everywhere has the same electron density, right? In this case, so this goes everywhere in space. Everywhere is 1 electron per meter cubed. I don't know, some density of electron. We can solve that system analytically for the exchange energy of that homogeneous electron. Okay, so that's just 1 electron with one space with a density of electron. Okay. Then you can do another space with less electrons. That's supposed to be less, right? It's a lower electron density everywhere in space. So that point is the same as that point, is the same as that point, is the same as that point. It's homogeneous. Everywhere is the same. Okay? The same as this water has density everywhere. It has homogeneous density, right? This electron is just like a homogeneous field of electron gas. Okay? Water has 1 density, and if I take, for example, ethanol, if I take methanol, if I take oil, right, they all have a different density. The same way, I can have an electron density with a high, homogeneous electron gas with a high density, with a low density, with a medium density, with any density. And for any density, I can exactly analytically calculate the exchange energy associated with that homogeneous electron gas. Okay, exactly. The correlation energy, it turns out, can not be calculated analytically, but using quantum Monte Carlo calculations on a similar calculation, you can on a similar system, you can derive the correlation energy of a homogeneous electron gas. Okay, and so what you end up doing is now, if I have, for example, an atomic center, and I have an electron, right, around electron density around that atom. Let's say it's got some density associated with it, which is changing, right? Maybe it's, I don't know, it's got some density. What I can do is I can say, well, I'm going to draw a box around that part, and I'm going to say that has, I don't know, 0.1, right? And I can draw a box around the point next to it, and that has 0.2. And, you know, as I go in, maybe that point in there is 0.8, right? I can say what the density of my electron is based on the density calculated from my non-interacting states. Okay, I can calculate the density, and I can tell you what the density is. But now, if I want to calculate the exchange correlation energy from the density, right, I can do it based on the homogeneous electron gas, because I know that a homogeneous electron gas with a density of that has a certain energy associated with it for the exchange and for the correlation. Okay, and say that's 0.8. What I do is I take a 0.8 density for that point. I calculate the homogeneous electron gas for the exchange and the correlation. Okay, completely separate system with that density. And then I sum. This becomes just a sum over homogeneous electron gases, right? So all of these points, so we're going to call those points P, right? Oh, well, okay, let's say all of space, R. So we're going over all of space, and at every point we have a density. And what we do is we just take the energy of the homogeneous electron gas, right, at the density at R. Okay, so the density at R is that. Feed it into the homogeneous electron gas with that density, get an energy, exchange and correlation energy, and when we've summed it up, we get our exchange correlation energy. Right? And so this is what's known as the local density approximation. Okay? All we're doing is we're taking a point in space, locally, feeding it into a homogeneous electron gas, and we're getting some energies which we sum over space, and that's an approximation to the exchange and correlation. It's bad in general, but for metals it works very well, where the electron density is not changing very much. Right? So if you have an electron in a metal, you know, the metal is smoothly varying, slowly varying. So if you imagine, well, I'm going to approximate some function of the density in terms of a Taylor series, right? If I do it in terms of a Taylor series, a power series expansion, well, if it's slowly varying, I only need the first order terms of the Taylor series expansion to get a fairly good result, right? And that's what the homogeneous electron gas is. It's the first order Taylor expansion of the functional of the exchange correlation in terms of the density. Right? We can go up to higher order expansions. We can include derivatives of the density, right? And yeah, this is how we do it mathematically. So I think I should probably stop there, right? I mean, I've already made you listen to me for longer than you're supposed to today. I think what we'll do is we'll catch up with this tomorrow. So this is supposed to be the DFT part of today, but there just wasn't enough time to go through all of the DFT today. So I think tomorrow what we'll do is we'll do the rest of the DFT. I mean, basically, we've talked about exchange and correlation. The next part of this presentation is really just about basis sets. Okay, so we've already basically talked about all of the components of DFT, all the mathematical components of the functional in DFT. But tomorrow we want to talk about how we can actually apply it to a crystal using an appropriate basis set, and also sampling over, for example, the Brillouin zone and all of the variables we need to consider. All right. Yeah. Let's end it there, and come back to it tomorrow. Yeah. Let me count you. 1, 2, 3, 4, 5, 6. Okay. So tomorrow we need to be on time, right? I mean, I need to finish on time. Okay. So because tomorrow what we're going to do is we're going to have the first 2 sessions, an hour and a half, and then we're going to leave this room and we're going to go over to the chemistry department and we're going to go to some computers, right? And we're going to do some calculations, maybe some programming, depending on what we decide to do tomorrow. But we're going to do some interactive things tomorrow for the second half. Okay, the first half is going to be more theory. Second half is going to be interactive. Unless you want to stay here, right? So there's 2 options. We can either go over and use the computers in the room, or if you have your own computer and you want to, and everyone's going to bring their computer tomorrow, we can do it on laptops here. Your choice. If not everybody has a computer available to bring with you, let's go to the room and do it there. I don't mind. So maybe I'll put a poll in the group, or maybe you can ask everybody, right, and decide what we're going to do tomorrow. Okay, just ask everybody and find out whether we're going to the other room or we're going to stay here. It doesn't matter. You try. Right. So let's stop. It's too long. It's too long.